Okay, 2012 AMC. This is problem 18 from the AMC12A. And it says triangle ABC has AB equal to 27, AC equal to 26, and BC equal to 25. Let I denote the intersection of the internal angle bisectors of triangle ABC. What is BI? Okay, so first off, I'm going to draw a sketch. I'm not going to make it too accurate, just a triangle where there are three different length sides. I'm going to try to make AB look longer than AC, look longer than BC. So let's draw it as carefully as I can. Okay. And it's clearly not right. Alright, so let's have this be A, B, C. And we know that AB is 27, AC is 26, and BC is 25. Okay. This next part, the intersections of the internal angle bisectors. Now, you might know what that is already. I'm going to just do a quick sketch of it. So, these are bisecting the angles. This bisects angle A or angle BAC. This bisects angle ABC, and I don't need to stop at the end of the triangle. It's just, I don't need to go farther. And this bisects angle C. Okay, and we are saying that this is the intersection. Alright, the first thing we need to know is that this intersection is actually called the incenter. It's the circle, it's the center of the inscribed circle here. Okay, and so that's the incenter. And you know about your intersections in a triangle. You have the incenter, the circumcenter, and the centroid are three that we usually cover. But we have this. On this, I will have some radii. I'm going to draw three of them. Of course, there are infinitely many radii, but they're all the same. And now, what we know is these are all tangent to that circle. So let's call this length here A, and the two tangents from a point to the circle will be congruent. Let's call these B. Let's call these C. And so what we're going to try to do is we're going to find A, B, and C. We're going to, and we can use a system to do that. We'll do that next. We're going to find the radius of this circle using Heron's formula and an incenter radius formula that I'm going to explain next. And then the final thing, I'm looking for BI. I'm looking for this length right here, which is going to be the hypotenuse of a right triangle with legs B and this radius R. So that's our idea, that's our plan. And so let's write this out. So we know that A plus B must equal 27. I know that A plus C must equal 26. And I know that B plus C must equal 25. And so, let's see, there are a few ways I can do this. Let me just let me add these two together. So I'll have A plus 2B plus C equals 52. Subtract this one to get rid of the A and the C. So I'll get 2B is equal to 52 minus 26, which is 26. So that means that B is 13. Okay, we'll use that later. So this is 13. 13, and I know this is 12, 12, and that means that this is 14, and 14, and you can see that all the way around the triangle. Okay, next thing, I need to find the radius of this circle, and of the inscribed circle, and I know that the radius, or the area of the circle will equal the radius of the incenter multiplied by the semi-perimeter, half of the perimeter S. And the reason is I actually have 3 triangles in here. This first one that I'm sort of outlining, this second one, and this third one. The sum of the bases of those triangles is the perimeter. The height of each of those triangles is the radius, and 1/2 base times height will give me the area of the whole triangle. Okay. I also know from Heron's formula, or Hero's formula, that the area is equal to the square root of the semi-perimeter multiplied by the semi-perimeter minus A, semi-perimeter minus B, semi-perimeter minus C. Okay, the semi-perimeter, half the perimeter, so let's see, 27, 52, 78. So the perimeter equals 78. Semi-perimeter equals half of that, which would give me 39. Okay, now let's put this in here. So the area will equal the square root of 39 multiplied by the semi-perimeter minus A. Semi-perimeter is 39. A is the side lengths, not these A's. That's a little confusing, but the 3 side lengths of the entire triangle. So these A's aren't those A's. My apologies, but whatever. On with things. 39 minus 27 is 12. 39 minus, well, I guess I should use that as A. B minus 26 is 13. And 39 minus 25 gives me 14. And I think, oh, that's a big ugly number, but it's going to be actually pretty easy if you look at the prime factorization of this. So the square root of 39 is 3 times 13. 12 is 3 times 2 squared. 13 is 13, and 14 is 2 times 7. So let's say I have 1, 2, 3 2's, so I have 2 cubed. I have 1, 2 3's. I have, let's see, a 7, and I have 2 13's. That's the prime factorization of this. And I can take out any perfect square, so I can take out a 2, a 3, and a 13. 2 times 3 times 13 gives me 78. I'm left with the square root of, and I had 1 2 left over, I had 1 7 left over, so I had 14. So this is the area, which is also equal to the radius times the semi-perimeter, so that's going to be equal to 38, sorry, not 38, 39, makes a whole lot more sense. R equals 78 root 14. So R will end up equaling 2 root 14. And now, finally, we have this triangle. The radius R, the leg length B, and we're looking for this hypotenuse. So I'm solving for, let me try to draw in the same orientation. So this is 2 root 14. This is 13. And this is my unknown, I'll call it x. So, Pythagorean theorem, that easy. 13 squared plus 2 root 14 squared equals my unknown squared. 169 plus, this one's going to be 4 times 14, which should give me 56. Let me double check that. Yes, okay. Equals x squared, and lo and behold, 169 plus 56 is 225, and it's a perfect square. Square root of 225 is 15. My answer finally is A.